In this segment, I want to talk about a couple of really interesting aspects of fluid dynamics. And the first is the continuity equation. And, this one's not too bad. I like to think of it as conservation of stuff. Because when I say the continuity equation and I give you some math, then it sounds like it's kind of tricky or hard, but it's not. It's just a pretty straightforward idea, and I think you'll agree with me. If I present it like this, I live in Fort Collins, and out here north of town, there's the Morning Fresh Dairy, and at the Morning Fresh Dairy, they make Noosa yogurt. And I don't know if you've had Noosa yogurt, but it's real good, right? And they make a whole bunch of it. It's very popular, national brand. They're making gallons and hundreds of gallons of it, right? And so over there at their factory, they've got this this pipe here, and it's a yogurt pipe, and it's coming along, and it's bringing in a whole bunch of yogurt. In fact, it's bringing in 10 gallons of yogurt every single second, okay, in this direction. So we got 10 gallons of yogurt going in this direction every second. And then what happens is the pipe splits. The pipe splits like this. Okay. And, we've got some that's going over here, and this is going to get made into pumpkin yogurt. This is the pumpkin yogurt pipeline. That's what this is. And so it's going over here, and it's not their most popular flavor. Only 2 gallons per second goes over there. Okay? Now, this pipe right here, this pipe carries the yogurt that's going to be strawberry yogurt. Everyone loves strawberry yogurt. We're going to need a little bit more of that. So we've got 10 gallons per second coming in here, and it splits. 2 gallons per second goes here. How much goes over here? What do you think about that? Pause the video if you have to. Well, hopefully you agree that if we've got 10 gallons per second coming in here, then we better have 10 gallons per second leaving, right? And so if we've got 2 gallons per second here, well, we must have 8 gallons per second right here, right? This is the law of conservation of yogurt. You maybe haven't actually learned this in another science class. I don't know. So we got 10 going out and 10 coming in. It just makes sense, right? How could you have anything else, right? If you've got something else, then you either have a hole in your pipe and you better go fix it, or I don't know, you got a cow in your pipe. Neither of those are true, right? So whatever we have coming in, we must have going out. I call it conservation of stuff. Your book calls it continuity. Either way. There's an equation for it. Let's look at the PowerPoint. The equation looks like this. It says that at any 2 points in a pipe or a tube or something like that, in any constrained flow, then the velocity times the cross-sectional area, that's the flow velocity, times the cross-sectional area, is equal to the flow velocity times the cross-sectional area at some other point. Now, let's take a minute, just a second, and look at those units. Let me erase the board. I'll be right back. Notice that each side of this equation has V times A. Now, when you put these square brackets around something, that's fairly standard, fairly common notation to indicate we're going to talk about units. So, what are the units of velocity? Well, the units of velocity are meters per second. And, of course, the units of a cross-sectional area are meters squared. And so, what do you get with a meter per second times a meter squared? Well, that's meters cubed per second. Well, meters cubed is a volume, isn't it? So this is volume per time. And so it turns out that V times A is an important idea. V times A is what we call the volume flow rate. It tells us how many meters cubed per second is flowing through this pipe. And so however many meters cubed per second of yogurt we have coming in this direction, we must have that exact same number of meters cubed per second leaving. And that's the idea of continuity. Again, I call it conservation of stuff. There's all kinds of great examples of this. And one of them is pictured here in this picture here where we see a faucet and water is coming out of the faucet. Now, this isn't in a pipe, but surface tension constrains the flow so that it stays together. You'll notice that, well, like everything, right? If I drop something, it speeds up as it falls, and water is no different. So as the velocity increases, the cross-sectional area goes down. In other words, you need a narrower tube of water. in order to transport the same volume if it's moving faster. So that's one good example. Here's a syringe. This is another good example of the continuity equation in action, right? Got this little syringe for giving my children medicine, and it's full of water here, right? And so if I was to squeeze this plunger here, then we'd see that the plunger is moving slowly, and so the water is flowing fairly slowly over here, but the opening of the syringe is much smaller, and so we expect the water to go much faster as it leaves the syringe, and indeed it does, right? So again, the area goes down, so the velocity goes up. The second important idea I wanted to talk about in this section is the Bernoulli effect. The Bernoulli effect is very interesting, and you may have learned about this at some point in your scientific education. But it says that where the velocity of a fluid increases, the internal pressure of that fluid decreases, which it's a little bit surprising at first. Now, in order to understand that, we need to kind of understand the idea of a streamline. A streamline is this imaginary line in a fluid flow, and it's the path that a massless particle would take if it was in the fluid flow. In other words, it's a fairly intuitive concept. It just describes how the fluid is flowing. If you're looking in a river and you dropped the tiniest leaf you could still see, just a tiny little leaf, and you just dropped it into the stream and you watched it flow by, it would follow a streamline. So Bernoulli's equation talks about relating the pressure and the velocity along 2 points on a streamline. Anywhere where we see streamlines bunch up, the flow speed increases, and therefore the internal pressure decreases. And examples abound. This is such an interesting concept, and it really is all over around us. Here's just a quick picture here to kind of describe it. As the wind is blowing over this little bump on the ground, well, in order for this to work, these streamlines have to bunch up over this little mound. Where the streamlines bunch up, the fluid is flowing faster, and therefore the pressure is lower. And we can see this all over the place. This is a classic example of the Bernoulli effect. I've got this piece of paper. It is not anti-gravity paper. It is regular paper. But if I blow over the top of it, observe what happens. Right? So what we saw here is that higher flow speed on top, lower flow speed on bottom, lower pressure on top, higher pressure on bottom. The page is pushed up from below. Another great example right here. This is a model of how a paint sprayer works, actually. If you've ever used a paint sprayer, this is basically how it works. I've got here a cup of water with a straw in it and another straw. I'm going to blow over the top of this straw. I'll do it nice and close. Hopefully you'll be able to observe something interesting. Oh, hopefully you could see that. I really don't know. I was focusing on my straw. Here we go. Hopefully I don't ruin my computer. Oh, yeah. Okay, I'm going to dry off my computer. Hold on. Okay, so what's going on here? Well, as I blew over the top of my straw, the airspeed here was much faster than the airspeed on the top of the fluid in the cup, right? And so as I blew across here, the airspeed was much higher, therefore the pressure was much lower, therefore the atmospheric pressure pushing down on the surface of the water in the cup pushed the cup up into the straw, and then when it interacted with the flow stream, it got sprayed everywhere. That's exactly how a paint sprayer works. These are fantastic examples of the Bernoulli equation, or of the Bernoulli effect. I haven't introduced the equation quite yet. Other examples include the flight of an airplane. Now, the flight of an airplane is more complicated than simply this, but this is a factor in determining how airplanes fly. An airplane wing is typically shaped like this. As the air flows by and over and around the airplane wing, the streamlines bunch up on top. Where the streamlines bunch up, the flow speed increases, the pressure decreases. So an airplane is pushed up from the bottom by higher air pressure. In a tornado, the roof gets pushed off of the house from the inside, right? We think of the roof getting sucked off by the tornado. It's not quite right? Because pressure only pushes. Pressure can never suck. Pressure can never pull. And so here we see fast air moving on the outside of the house. Fast air, high velocity, low pressure. Inside the house, the air is still. Low velocity, high pressure, the roof is pushed off from the inside. This is one of my favorite examples. Groundhogs, I'm not a groundhog expert. However, I am told by this textbook that groundhogs will build one side of their burrow with a taller mound than the other side of the burrow. What does that do? Well, it makes the streamlines bunch up on this side here, creating higher velocity, lower pressure, and so you get a nice breeze through the tunnel, right? So whenever the wind blows up here, it also blows through the tunnel. Now that wouldn't happen if you didn't have different shaped mounds on both ends of your burrow. So that's a pretty interesting example as well. So here's the equation. We already have learned that pressure changes with depth in a fluid. And Bernoulli's equation combines this idea that pressure increases with depth the farther down in a fluid you are, and it also decreases with increasing velocity. Okay, so we put those two ideas together, and we end up with Bernoulli's equation. And it compares 2 points, again, along a streamline. We don't need to get too worked up about the streamline. I'm not going to be asking you subtle questions about whether or not things are on a streamline. But that is the idea. We're comparing 2 points along a streamline. And the sum of all these parts must be constant along any streamline. What are these parts? Well, this is the pressure. So the pressure at point 2, 1/2 rho, that's our density, right? V is the flow speed. Rho is density. Good buddy G, that's 9.8 meters per second squared, as always. Now Y is the height above some reference, right? So notice Y1 and Y2, well, they're just two heights above some reference. Again, you're going to need to decide what are we calling Y equals 0, as we did many times in previous chapters. Okay, there we go. One other thing to point out about this equation is these two terms should look familiar to you. 1/2 rho v squared. Gosh, it's reminiscent of something. Well, 1/2 mv squared is, of course, kinetic energy. And rho is simply mass per volume. Okay, so it's very similar to kinetic energy. How about this one? Also very similar to potential energy, isn't it? Right? Potential energy, gravitational potential energy, recall, is mgy. And so we can interpret this as the kinetic energy per volume, and we can interpret this as the potential energy, the gravitational potential energy per volume. Pressure is a little bit harder to interpret in terms of energy, but really, Bernoulli's equation comes down to conservation of energy. It really is conservation of energy per volume. And if we understand it as that, then we can see that, well, it's not really that different from what we've seen before. You know, another kind of useful, I think, way to interpret Bernoulli's equation and this idea that the internal pressure must be lower at higher velocities is think about this syringe again. And if I push on this side here, then, of course, we're going to have slow-moving water here and fast-moving water as it exits. So doesn't that mean that the water accelerates as it moves from the wide part of the pipe to the narrow part? Yeah. We must have an acceleration in this direction. Therefore, we must have a net force on the water in this direction. Oh. If I'm going to get a force in this direction, I must have higher pressure here and lower pressure here, right? This fluid is going to accelerate towards areas of lower pressure. So it's just another way to sort of remind ourselves and wrap our brains around this idea that the internal pressure decreases with increased velocity. Okay, let's do this example. Water flows through these pipes as shown in the PowerPoint. The water speed through the lower pipe is 5 meters per second, and a pressure gauge reads 75 kilopascals. What is the reading on the pressure gauge in the upper pipe? Okay, so we're going to look at this and we're going to say, okay, we've got a fluid flowing through a pipe. I've got changes in height, and I also have changes in cross-sectional area. And that means I have changes in velocity, right? So that means I want to use the Bernoulli equation. So let's just go ahead and write that down for starters. Okay, so now we've got Bernoulli's equation written down. We can see that we're going to have to compare the velocities, aren't we? Now notice that we've only been given one velocity, and so I think in order to proceed here, we better find that second velocity. Why don't you think to yourself, should the velocity be greater or less than 5 meters per second? Notice the velocity is 5 meters per second at point 1. What is it at point 2? And we're going to calculate a number in just a second, but go ahead and predict, should it be greater or less than 5? Well, hopefully you decided it should be greater, right? The pipe narrows, so the cross-sectional area is lower. Therefore, the flow speed must increase. In order to figure out what that is, let's go ahead and use the continuity equation. Solving for V2. Okay, so I've got my continuity equation going here. Notice my pi's cancel. Some of you might be saying, hey, why didn't you convert these to meters? Yeah, I've got centimeters on the top, centimeters on the bottom. The units cancel. It doesn't matter what units I use there. And so we ended up getting 11.25 meters per second. Okay, so now we know the velocity in that upper pipe. Now we can go ahead and apply Bernoulli's equation. And we are looking for the pressure gauge reading on the upper pipe. So that means we are looking for P2. So the first thing we're going to do is we're going to do some algebra, and we're going to isolate P2. I've isolated P2, and I've kind of bunched these together. I'm going to go ahead and do some factoring. It's going to make it easier for me to run my calculator, and more likely I'll get the right answer at the end. Okay, there we go. Now I'm going to go ahead and plug in my numbers. We'll see what we get. Notice they didn't tell us what the density was, but it tells us water, right? And we know that the density of water is 1,000 kilograms per meter cubed. I'm going to have to do a new line because I'm out of room here. Okay, so now I've plugged in my numbers. Nothing too tricky. Maybe one point I should make here is, notice I've set my reference level, right? I've gone ahead and I've said the lowest point in my problem is y equals 0. We did this a lot when we were doing conservation of energy. So the lowest point in my problem is 0. That would be y1. So we set y1 equal to 0. That makes y2 2 meters. I've plugged in. Now I run my calculator, and I get an answer of 4.6 kilopascals, or 4,600 pascals. Okay, not too bad. Notice we put in a gauge pressure, so we'll get out a gauge pressure. Now you have to be a little bit careful with that, because we're adding pressures here. Had we added 1 atmosphere to P1, then we would have ended up getting the absolute pressure for P2. But it asked for what the pressure gauge reads, so we would have had to subtract that back out in order to get P2. Since all these terms are added here, we don't need to worry about that, right? So Bernoulli's equation works equally well with gauge pressure as well as with absolute pressure, as long as you recognize what you're looking at. One other note I was sort of fast and loose with my units a tiny bit here. I wrote 75 kilopascals. I didn't enter this into my calculator as 75, right? I entered this in as 75,000, right? Because pascals is our standard unit. So 75,000 pascals. And of course, my calculator didn't tell me 4.6. My calculator told me 4,600. I wrote it as 4.6 kilopascals because it's just a little bit more efficient.